Today we are going to discuss about Malus law. This is Malus law. So this is a very important law. Now regarding this one, throughout this particular topic of polarization, we have been discussing about production of a plane polarized light. Normally when an unpolarized light is incident on the plane of a polarizer, then the transmitted light is supposed to be a plane polarized light. When an unpolarized light is allowed to incident on the plane of a polarizer, the transmitted light ray is a plane polarized light. Now when that plane polarized light is incident on the transmission of an analyzer, then the intensity of the polarized light is supposed to be varied, and it varies with respect to the cosine of the angle of the plane of the transmission axis of the analyzer and the plane of the polarizer. Now we write it here like this: when an unpolarized light is incident, when an unpolarized light is incident through the polarizer, then the transmitted light ray, is a plane polarized light. So you are taking a unpolarized light, and that is supposed to be incident through a polarizer. Then what does it do? It will polarize that. Polarization means what? Making a change of the unpolarized light to a polarized light. So that is what we are saying it with respect to a statement. Now what we are doing here, this polarized light, that is the plane polarized light. The plane polarized light is transmitted through an analyzer. Then the intensity of the polarized light, transmitted varies between the angle of plane of polarizer and between the angle, that is, it varies between the angle of plane of polarizer and the plane of transmission of the analyzer. So this is the generalized statement what we are giving here. Therefore here the second part of that, so when a plane polarized light is supposed to be incident on a analyzer, on the plane of transmission of an analyzer, then the intensity of the polarized light varies as the cosine of the angle between the plane of transmission of the analyzer and the plane of polarizer. So that is what the statement is according to Malus law. So writing the statement, after considering these following facts, we will write the statement as a simplified statement is written over here. According to this statement, we say that Malus law states that the intensity of the polarized light, transmitted through the plane of transmission of the analyzer. Malu's law states that the intensity of the polarized light transmitted through the plane of transmission of the analyzer varies as the cosine of angle of transmission of the plane of the analyzer and plane of transmission of the analyzer and the plane of the polarizer. So this was what we have already stated regarding this statement. So it states that, let me repeat it again, the intensity of the polarized light transmitted through the plane of transmission of the analyzer varies as the cosine of the angle of transmission of plane of the analyzer and the plane of the polarizer. So this is how the statement is all about. Now let us give a diagrammatic representation for this. So in this diagrammatic representation, here the proof is stated as follows. Now here we are any amount of a light ray which is undergoing either polarization or analyzation. We are talking about an incident light ray. That amount of an incident light ray is resolved into two components. So here we are saying that any polarized light can be resolved into two components. So here any polarized light is resolved into two components. What is the first one? First one is the plane, any polarized light is resolved into two components. One is parallel to the plane of transmission of the analyzer. Number two, perpendicular to the plane of the analyzer. So this is how we resolve the polarized light into components. Parallel to the plane of transmission of the analyzer, and the second one is perpendicular to the plane of the analyzer. So for this one we are representing a diagram here. For the representation of a diagram here, we consider capital A as the amplitude of the incident plane polarized light. We consider capital A as the amplitude of the incident plane polarized light. Now here we are resolving it into two components. That is, with respect to the optic axis is what we take, and also the analyzer axis. So here we are resolving that here like this. So this is a state of representation. Now here we are drawing a circle. This is your incident light. Okay, this amount of incident light possessing amplitude A. Now this is your analyzer axis. So this is your analyzer axis. Okay, these what we call the representation is what we are saying here is one is taken as a parallel component, the other is a perpendicular component. Parallel component means when this analyzer, which is moving with respect to the parallel to the plane of transmission of the analyzer or the polarizer, then this is one which is perpendicular to the plane of transmission of the analyzer. So this is how we resolve them into two components, where here with respect to that, the amplitude of the plane perpendicular to the plane of the analyzer, we are taking that component as A cos theta. The component with respect to the amplitude which is supposed to be perpendicular to the plane of the analyzer is taken as A cos theta, or simply we can say that A cos theta is the perpendicular component which is supposed to be the perpendicular component with respect to the plane of the analyzer, and the parallel component is taken as A sin theta. Now the amplitude of the incident light with respect to the plane of transmission of the which is perpendicular to the plane of the analyzer is taken as theta over here. Now this theta is what we are saying, it keeps on varying between the plane of transmission of the analyzer and the plane of the that is with respect to the plane of the polarizer. So in this way we are representing or resolving that into two components. Now here what is that we said, according to the Malu's law, we are mainly talking about the intensity of that polarized light, and that intensity of the polarized light is what we say that it is varying with respect to the cosine of the angle between the plane of transmission of the analyzer and the plane of the polarizer. So now let us take that particular point and consider it. So let us say that the intensity of the polarized light, the intensity of polarized light along the perpendicular component, or with respect to the perpendicular component, is taken as I1. So I1 is supposed to be the perpendicular intensity of the plane polarized light with respect to the perpendicular component. Then that is given by, as we know that intensity is supposed to be always proportional to the square of the amplitude. Now A cos theta is the resolved component. A cos theta is the resolved component with respect to the perpendicular axis. So that we write it as I1 is equal to A cos theta whole square. Let us consider this as equation 1. This equation 1 we can transform it as I1 is equal to, squaring it, we have A square cos square theta. So I1 is equal to A square cos square theta is the component. Now here, as already we said that they are resolved into two components, one parallel to the plane of transmission of the analyzer and perpendicular to the plane of the analyzer. Parallel component means what? Accordingly we can say that according to case 1 means which is called as a parallel component. Parallel component is the one if the angle between the plane of the analyzer and the plane of the polarizer is supposed to be 0. 0 means when theta is supposed to be 0, we say that it is parallel to the plane of the transmission of the analyzer. So it is almost with respect to the plane of transmission of the analyzer. So that particular component, here we can say that when theta is supposed to be equal to 0, when theta, it doesn't make any kind of an angle there. Then when theta is 0, substituting the value of 0 here, then what? Then I1 will be equal to A square, cos 0 is 1, so I1 will be equal to A square, since cos 0 is equal to, cos 0 degrees is equal to 1. So I1 is proportional to A square, square of the amplitude. Okay. Now this is for that with respect to the what, when theta is equal to 0 degrees. Now the same we can say that if we consider I0 as the maximum intensity, if we consider that there is maximum intensity there at that particular point, then we can write it as I0 is equal to A square also. So the maximum value of intensity will also be directly proportional to the square of the amplitude. So that is what we are terming it over here. Now substituting it in equation, say let us call this as 1a, then we have substituting I0 which is equal to A square in equation 1a, we have I1 is equal to, what is a square, which is I0. So I1 is equal to I0 cos square theta. So this is for what? With respect to the maximum intensity, we are taking to explain about the angle with respect to the intensity at a particular point, which is supposed to be, theta is supposed to be equal to 0, and when there is existing maximum intensity. Then next, with respect to the same thing, let us resolve it for the second component, that is for case 2. Case 2, in the sense, this is concerned with when theta is supposed to be equal to 90 degrees. Now here we have I1 is equal to a square cos square theta. Theta is 90. So cos 90 is what? 0. So this entire thing belongs to completely rounded off to 0. Therefore, when theta is equal to 90 degrees, then I1 is supposed to be equal to 0. So theta is 90 degrees means what? Perpendicularity. So perpendicularity, then the intensity is supposed to be equal to 0. So this is what we are referring it in terms of the values. So in that particular sense, I1 is supposed to be equal to 0. When we substitute the value of theta as 90 degrees, we are getting it as I1 is equal to 0. And in the first case, I1 is supposed to be equal to square of the amplitude. So that is how we assess the cases for both these things. Then next, coming to the equations we have, let us term this value as equation 4. Now, from these respective equations, it is clear that the intensity of the transmitted light passing through the plane of transmission of the analyzer varies as the cosine of the angle between the plane of transmission of the analyzer and the polarizer. So we can write it as, from equation 4, it is clear that the intensity of polarized light, transmitted through the analyzer varies as the square of cosine of the angle between the plane of, we can call this as vibration, because the particles are vibrating either perpendicularly or parallel. So angle between the plane of vibration of incident plane polarized light and optic axis of the analyzer. So this is how we are calling this one as the optic axis. So you can see this is analyzer axis, which is also termed as the optics axis. So that is how we can say that if a component varies with respect to the angle, then the intensity is directly proportional to the square of the amplitude, or the intensity is supposed to be equal to 0. That is with respect to the cosine of the angle with respect to the plane of transmission of the analyzer and the plane of the polarizer. So this is how the statement of Malu's law